Yeah. They're actually really simple, but the problem is that they don't present you with everything here. Like they just tell you these are phasors and work with them.
Yeah.
I mean, there's a whole lot of things going on with phasors that they don't tell you about, which you talk about it in circuits too. It's this one, or
yeah, that one.
Which one are you confused about?
Actually, the first one.
First one?
These ones are pretty straightforward. But yeah, the first one.
The series are also circuit. What are you confused about? Do you know what's going on with phasors?
I think that's what I understand. Maybe.
So I'm not gonna do the physics bit. I'm just gonna try to. I mean, you can get my physics stuff. I can show you the concept. You can get my.
Right. Yeah, I understand that.
So I'm not gonna do it the plug and chart way.
Yeah.
Oh, I think I need to.
That's the thing. It's like I know how to do it using just the equations.
Yes.
And like, but I don't understand it conceptually.
Right. Okay. So you didn't take circuits one, but I assume you know enough about circuits one from physics now. So. Okay, there we go. So, normally, when you have a voltage variant, I mean AC, what's different about AC and DC is that in AC you have a voltage that's varying over time. Right? Mm-hmm. It's not the same as, I mean in DC sometimes you also have a voltage varying over time, you do not get down. This font, whatever. When it's described as T is equal to 1 minus e to the negative T over tau or whatever, it doesn't matter. The important thing is that the voltage in the circuit is a function of time. In our case, when, in the AC case, the voltage is also V of t is equal to some value times cosine of omega t, something. It's a function of time. Omega t, omega is the frequency, which is, so this is your sine wave for the AC circuit, right?
Yeah.
So higher frequency means
closer together.
Right, closer together, and lower frequency means further apart. So this is called the time ring, as in you're working as a function of time. Right. The circuit behaves differently at different times. At t equals 0, it's going to have a different voltage than at t equals 1, at t equals 2, at t equals 3, etc., etc.
Right.
Now, they solved these equations and they did a bunch of shit when, I shouldn't say that. They did a bunch of stuff.
You're being recorded.
So they did Kirchhoff's law here.
Yeah.
And they found out that the voltage is given by whatever across this, and C is equal to dV by t, where Q is equals I is equal to C dV by t, and L is equal to whatever. And they found equations for all of them. And what we found out is that the current through the inductor varies with the voltage across the inductor varies with the current across the inductor by 90 degrees. Because when you derive, so this is a cosine function, right? Right. This is let's assume it's cosine. Assume the 0, B is given by B0 cosine omega t. So for AC, I'm going to let's draw this one in black. The voltage is going to look something like that, okay? For an inductor, it's I is equal to L, D is equal to L divided by dt, right? That means we want to find, well, here, capacitor, I is equal to C dV by dt, right? Well, let's assume this is the current in the circuit. Let's assume this graph is the graph of the current in the circuit, okay? Right. The current is given by a certain, it's called, let's say the current in the circuit is given by I see omega t due to this alternating source. They're all alternating at a frequency of omega. So this is alternating at a frequency of omega given by cosine omega t. The voltage across the capacitor is the integral of I, right? Because I is equal to c divided by c. They all share the same current, by the way. It's obvious, right? They're not serious. So the integral of that, the integral of a cosine function is sine, right? So sine function goes like this. Right? These are 90 degrees. This is the voltage across the capacitor is the derivative of the current, right?
Yeah.
The derivative of the cosine function is
Also sine, but negative.
Negative sine. So this is your sine. Negative sine would look something like that, right?
Yeah.
Across here, and go like that. And the voltage across your resistor is just V by R. So it's going to have the same graph as this, but amplified plus or minus, right?
Right.
Because you just multiply it by constant, so it's not going to shift anywhere. Now, these are your three graphs. This is the voltage across the resistor, voltage across the capacitor, voltage across the inductor. We found out that when they're connected like this in series, the voltage across the capacitor is always going to be, well, I'll explain what this is in a bit. This is just to remember. The voltage across the capacitor is always going to be lagging. Is it lagging or leading? Capacitor is negative. Therefore, the voltage across the capacitor is always going to be leading the current. Lagging. The voltage across the capacitor is always going to be the current by 90 degrees. This is the voltage across the capacitor. Yeah, it's 90 degrees. This reaches its peak here. This reaches its peak here. So this is 90 degrees behind. This is lagging by 90 degrees. And the voltage across the inductor is leading by 90 degrees. Lead, here's the lag. Right? Okay. So they're always 90 degrees apart.
Right.
And this is actually always the case. So voltage across the capacitor is always 90 degrees. There's always a 90 degrees difference between the voltage across the capacitor and the voltage across the inductor and the current.
Okay.
And this also obvious when you draw the pictures. This is a 90 degree difference. This is a 90 degree difference. This is what you see. This is the L. This is the current, which is B. It's in phase. The current is in phase with B bar. Because we just said B bar. Right. There's a 90 degree difference in all of that. So instead of working with a time domain, they decided to introduce a new domain. So now we're no longer working as a function of time. Because everything in your circuit, so I mean, this is going to go on forever, right?
Yeah.
And we know it's going to look exactly the same. So why do we keep on asking, what do we have at this time? And what do we have at this time? And what do we have at this time? We know everything's going to be the same. The only thing that's different is one period. One period is all we care about.
Right.
Everything here, we know what it's going to be. Right? Because we just copy this graph, put it here. Copy that graph, put it here. Copy that graph, put it here. It's all going to be the same. So what we decided is not care about time. Turn everything into the phasor domain, which is the frequency domain. So everything in your circuit is going to be a function of omega, the frequency. For a certain frequency, everything is going to be the same. They're going to be 90 degrees apart.
Why?
They're always going to be 90 degrees apart.
Okay.
Because
of your
equations. Because your equations I is equal to c divided by dt.
Yeah.
The derivative of a sine is always cosine.
Okay.
The derivative of cosine is always negative sine.
Right.
It's 90 degrees apart.
Yeah.
Right?
Yeah.
So everything in your circuit is always going to be the voltage across.
Yeah.
I say everything in one.
Yeah, I know.
Yeah.
Okay.
Why
do you use frequency? Or
why we use frequency?
Yeah.
Because it makes calculation so much easier. The phasor domain is actually a complex number domain. they don't introduce it in physics because they assume you don't have a background in complex numbers yet. But in reality, phasor domain, what it means is this is actually a complex plane.
Okay.
So this is the real axis, and this is the imaginary axis.
Okay.
Okay. So what you actually do with phasors is you transform everything. So originally this was v of t, and the voltage across here would also be v of t, the L of t. Voltage across here is going to be VR of t, and something here is of t. You transform it from v of t into a phasor. So that means, so here's how you transform it in phasor. And it actually makes a lot of sense. It makes life a lot easier. So v of t is equal to v0 cosine omega t plus some angle displacement phi. Okay. The spatial representation is, let's make confuse you at first. V0. In complex analysis, this means e to the negative, e to the I, or I is the imaginary number. Do you know what e to the I is?
Is it something with pi?
Cosine, yeah, cosine, e to the, so e to the I theta equal to cosine theta plus I sine theta.
Okay.
Okay.
Gotcha.
So V0 is actually, it's actually the real part of this.
Okay.
Okay?
Gotcha.
It's the same thing, right? The real part of this is just the one without the.
Right.
The real part of a complex number, if your complex number z is equal to x plus iy, the real part of z is just x, right? The imaginary part is y.
Okay.
Right?
Yeah.
So the real part of this, V0 e to the I theta, is just this original one, V0 cosine omega t plus phi.
Huh.
Well, actually the real part of to be times e to the negative. You take that out for simplification, and we just do calculations where we actually only do calculations times this. 0. You turn everything in your circuit into phasors, into complex numbers. Now, everything is a complex number. That's a phasor domain, a complex number. Everything is a function of frequency. What it means is, when I say a function frequency, as in.
Yeah, that's what I'm trying to understand. What do you mean by function?
What's going to be different? Because, look, so your entire circuit resonates at a frequency at the same frequency as the source.
Right.
The source, if the source has omega, notice how everything else here had omega in its cosine omega. The derivative of it is something omega t, right?
Right.
Omega t.
Yeah.
Omega t. So there's only one frequency. So, and the impedance of your circuit is going to depend on the frequency also. So, right. The impedance of your capacitor. You remember how XL is equal to XL is equal to omega L. Right?
Yeah. So XL. So that was another thing I was confused about as far as notation. What is XL and XC?
XL is the complex impedance. So it's a complex resistance. It's called reactance. So
it's called what?
Reactance.
Reactance?
Yes. So do you know how so in DC analysis, right? When you have a resistor, it decreases your current, right?
Yeah.
In AC analysis, when you have a capacitor, what does a capacitor do?
Well, it decreases your current at first. Or no, it decreases your current after a long time.
Let's say you have, forget about DC, now we're in AC, capacitor in AC.
Yeah.
Let's say you have this signal and this signal.
Okay.
One with higher frequency and one with higher frequency and one with lower frequency. Okay?
Right.
Now, if you try to, well, do we want this to be current, or actually we want it, let's say we want it to be voltage or current that would make it easier.
Okay, wait, I have another question.
Yes.
EMF, right, is a vector?
In the complex domain, yes. Because every number in the complex domain can be thought of as a vector.
Well, okay.
I mean, because you're working in the real plane and the imaginary plane, right? So if you have the number z is equal to x plus iy,
Yeah.
it's going to be x here and y here. You can also represent it as a vector.
Okay.
Yeah?
Yeah.
From the origin to here.
Okay.
So that's why all these things, these phasors are basically vectors.
Okay.
In the imaginary and real plane. We imagine that they're spinning.
Why wouldn't they teach us complex numbers and then teach us physics?
They teach you, well, they don't even teach you computer circuits.
Exactly.
I mean, they just give you a background on complex numbers in the beginning circuits.
Right. It would be so much more helpful if you already knew complex numbers. Going into this or going into, like, I don't know. I feel like math should be taken care of first in education. I don't know, sorry.
No, they should.
Because I only
think that stuff a little more. You don't.
like when I took AP Physics the first time in high school, I was completely lost because I was taking calculus at the same time, so I was just learning it like randomly.
Right.
And like so things we learned at the end of calculus, I was like, oh shit, this would have been so much more useful like at the beginning of physics and stuff. I'm like, I don't know. It bothers me. Math should be out of the way first.
You should at least give a review of the math that you can use at the beginning of every class. Even if I don't even care if you even give a, like, I don't even think we need like calculus courses. I just think that half the course, the beginning should be like, all the new math concepts that you're going to use, understand that, and then move on to the course.
Right.
I don't know, there's different ways to do it, but you're really bad thing. But anyway,
Continuing, sorry.
so that's fine. So if you have two signals, let's say they're voltage, both work the same way. So if you have, what does this mean? So you have a voltage source here. Okay, you have a voltage source here that's connected to a capacitor. One of them looks like this. When it's here, it's going to try to push current in this direction, right?
Right.
When it flips, it's going to it's going to flip the polarity and it's going to try to push current in that direction, right?
Right.
This one, the one with the low frequency, what is it doing? It's pushing current here, and after a while, let's say T1, it flips. The longer your T1, what happens to the capacitor first?
So at first it's a wire.
Short circuit, right?
Yeah.
After a while, After a while,
Yeah.
it's going to be open circuit, right?
Right.
So the longer you take, the higher the impedance of the current becomes, because current is decreasing. Remember, the second you close the switch in an AC circuit, the second you close the switch, the capacitor short circuited, right?
Yeah.
So that means you have no impedance. The current, the capacitor is not doing anything.
Right.
It's basically letting all the current pass through. But after a long time, it's blocking all the current.
Right. So
the longer you're pushing in the same direction,
right.
the bigger your capacitor is resisting, the more resistance the capacitor is making against the current.
Okay.
So here, you have short. So you're pushing in short time intervals. You're only pushing in one direction this much. So the capacitor is not completely filled up. So it doesn't resist all the current. It flips before the capacitor is completely charged. Flips before the capacitor is completely charged.
Right. Yeah.
Short circuited again. And then the impedance of the capacitor starts decreasing. This is why X of C is equal to 1 over omega C for the capacitor. Because at higher frequencies, it doesn't impede as much.
Okay.
At lower frequencies,
It
it impedes more. Because at first it's a short circuit.
Gotcha. Okay.
Right? The inductor is the other way around. Because the inductor at first, it's an open circuit. Right?
Right.
So the longer you take, the less its impedance is going to become. That's why at lower frequencies, your impedance is going to become lower for the inductor.
Gotcha.
Right?
Yeah. Okay.
So this is what this means. It's so the current. I mean, the current in the circuit is actually decreasing due to these. Although they're not dissipating any power, they're just storing them, but it's still decreasing. They're still affecting your current. That's why we define them the same way you define resistance. We've been using the unit ohm for them, right?
Yeah. So basically, these things are like the individual.
It's like the resistance.
It's like the It's like the so Z is like the impedance of the whole thing.
Z is the impedance of the whole thing.
And then each one, like C is like the impedance of one element of it, basically.
So they have different effects on the current.
Right.
Okay. So a resistor, what it does. So if you have let's say you have.
Actually, wait. Z is just the addition of all the components.
Z is equal to, well, in reality, Z is equal to R plus, again, the imaginary number I plus IX. Actually, it's the reactance in reality. And this is why Z squared is equal to R squared plus X squared. So forget about this for now. Just work with this.
Okay.
Is this right? Yeah, Z is equal to
square root. Yeah. So you're just adding those, like, so if you have a phasor diagram, you're adding the components of it. Isn't that what Z is, kind of? Like you're taking the magnitude.
The vector sum.
You're taking the magnitude of the components.
Yeah, because again, complex numbers.
Right.
So you're adding a complex number that's in that direction, a complex number in that direction, and a complex number in that direction.
Okay.
So a complex number here, complex number here, complex number here. This one's always going to be here. Yeah. This one's always going to be here because it's off by 90 degrees.
Right. Yeah.
Always going to be here because it's off by 90 degrees, and the other one's always going to be here because it's 0.
Okay.
Degrees. Now let's say you have this current, okay?
Yeah.
And you place a resistor. If you place a resistor, this is the effect it's going to have, right?
Right.
Right.
Yeah.
So that's how it affects. That's how it impedes the current. Just
right.
reduces it. When you have a capacitor or inductor, though, it's going to create a phase shift. So, because again, from that equation that we just found, sine, when you derive it, it's going to be a cosine.
Right.
That means it's a 90-degree phase shift, 90-degree out of phase. So when you add a capacitor and inductor, the original one, I'm not looking at this one now, the original one, it's just going to move it.
Okay.
Okay.
That's not the current for the whole circuit.
No, that's just the.
That's the current across the inductor.
That's how much. I want to say that's how much the inductor. That's how the inductor wants the current to be. That's the voltage. That's a voltage across one of the elements. That's a voltage across the capacitor and the inductor. Okay. It's easier to do in terms of voltage. This is the voltage. This is the original voltage. The voltage of the inductor. Well, it's going to have phase. It's going to look something like this, right? So now the sum of this, the sum of these, is going to be here. So this minus this, it's going to look something up here. This minus this is going to be somewhere here. This minus this here. This minus this is going to be about here. This minus this here. This minus that is going to be somewhere here. This minus that, etc. I don't know. Well, it should be the same frequency. I don't know. Something wrong there. Just not versus. Now that's another point. It goes something like. Yeah, that makes sense. Something like that. So the magnitude of the original signal, which is this, the black one, did actually reduce, but it's not the same way as it was reduced in a resistor. It's not because you have less magnitude. It's like you haven't really lost it, but it's at a different time interval.
Okay. Gotcha.
And because when you're doing Kirchhoff's law, you're subtracting voltages, right?
Yeah.
So you say, okay, you have a voltage gain across the battery, and then a voltage drop across the inductor, resistor, or capacitor. That's why I was using it. That's why I was subtracting.
Okay.
You have a voltage loss across this inductor or capacitor.
So the red line.
The red line is the
voltage after you added.
Voltage after.
Like after you added an element or something. Okay. Gotcha.
The red line, it kind of represents the current in your circuit. If you had a circuit like this, and the voltage across this is going to be the voltage of the source minus the voltage in the inductor, right?
Yeah.
It's going to be some constant times the current.
Yeah.
So in this case, it represents the current. So I'm always assuming that we don't really have any circuit that doesn't have a resistor, because we run into problems if we do. If you just connect a battery across an inductor and you assume completely ideal wires, you're going to run into problems.
Okay.
But when you imagine connecting two batteries together.
Right.
And confusing these pictures because it's like some confusing.
Okay.
It's just for steady state analysis, so which means, so I mean, the second you connect the source, you remember how in DC, if you were taking circuits, this would be easier for you.
Right.
So when you connect, so the voltage across the capacitor looks something like that. This is when you connect the switch, right? When you close the switch. And this is after it's completely charged.
Okay.
Right?
Yeah.
This is called transient. This is the small part, what happens like in 0.00000 whatever seconds.
Right.
And this is the steady state. This is the long time effect.
Yeah.
So this, if you're in the lab, this is what you actually measure by hand without using the oscilloscope or any advanced instruments. What you measure with a multimeter. So let's say you connect a circuit and you have capacitors and inductors and whatever.
Right.
And after 1 second, you put your voltmeter to see your voltage across it, you're going to get something here. It's not going to tell you anything about here because it's not fast enough. And this is what you usually deal with. Now, the phasor only tells you about steady state also. There is some stuff happening right when you close the switch and right when you turn your AC source on. It's getting up to the value, so it doesn't start. It doesn't start off.
Right. That's not immediate.
Yeah, it goes something like that.
Yeah.
But we only consider
Okay.
this. Yeah.
Okay.
And look at this. Last thing, I think they told you this. Oh yeah, they did this for you in the pre-lectures. So remember how I told you that we don't want to keep working with the time domain because one period is enough to describe the entire circuit, right? All you need is one period, right?
Right.
And so this is a period. So this starts here. Spinning this phasor 360 degrees is one period, basically, right? Because you saw how that thing at the reaction happened. As these were spinning, it was drawing a sine wave, right?
Yeah.
So the phasor just describes the relationship between the elements. So how far they are apart. Because we know for a fact that it's not going to change with time. They're always going to be the same distance away. The impedance of the resistor, the impedance of the inductor is always going to be this much because you're working at a certain frequency. Yeah, frequency domain. Working at a certain frequency, you can't change the frequency. The impedance of the capacitor is going to be always this much because you're working at this certain frequency. And the resistor is always going to be a resistor.
Yeah.
Right?
Yeah.
So this tells you everything you need to know about the circuit in steady state. Because nothing's changing. And at any given time, you can always convert this back to the time domain if you want to know something at any given time. But this in reality, like when you look at it like this, it doesn't really tell you what's happening at time t equals 5. Right?
Yeah.
It just describes everything that's happening in one period, like one diagram.
Okay.
So that's everything that's happening in the period.
Gotcha. All right. Can you go back to the homework?
What?
Can you go back to the homework? There were. I can remember there were a couple. But like, I don't know. There's still. So go to. I remember now in AC. So go to 1.
1?
No, the second one.
Oh, the second one? The second one.
Second AC section.
Yeah.
Yeah. Okay. No, not 1. Not 15. So what's one of these? Okay. 3. 3 and 4 actually. Both. Just these particular questions.
Okay, you found I and X.
Uh-huh. And the impedance.
And you find the impedance of the circuit.
Right.
So far you have. So far we have. Oh, whatever. What do we have here? A circuit is constructed in AC. Okay, we have this. We have a magnitude of it. We have omega. We have R. We have L. We have C. So we know. Oh, do we not? Oh, we know omega. Okay.
Yeah.
So we know so far. What we know so far is. Your Z, your R, your L, your C, right? You know,
Is that XL?
I'm going to start reading. And you know the magnitude of I, and you know the magnitude of B and F, right?
Right.
And the phase angle between the generator voltage and the current in this circuit. Okay.
Yeah. Yeah.
Yeah.
Yeah. So what is that angle? Right, where is it? I guess.
This is VR, this is VL, this is VC, right? And we have a certain EMF here from the generator, EMF G. Okay. So what this is saying is that at any given time, the EMF that's supplied has to be lost across this element, and this element. So the sum of these has to be this, right?
Right. Yeah.
Kirchhoff's law.
Yeah. Got that.
Okay. So, and the more general, V is equal to IZ.
Okay. I don't know if they gave us that.
What?
I don't know if they gave
Did I
us
do
that.
that?
It makes sense, but I just don't think they provide that.
When you're working in the phasor domain, this makes sense.
Okay.
They don't give you that, no? How do they expect you to do this? Well, I guess they go straight ahead and tell you that this is the same angle phi. I was just trying to make that connection.
Okay.
Do they just tell you 10 phi is equal to, do they tell you that 10 phi is equal to?
Yeah, 10 feet is, yeah.
XL over phi, or XL over R?
XL, yeah, XL minus C over.
Oh, XL minus C over
yeah,
R.
yeah. That's what they tell us.
Well, yeah, I mean, that's because this angle's here, right?
Yeah.
And G is equal to IZ for anything.
Right.
So VC is equal to I Z. The Z is only XC, XL, by R.
Right.
So I mean, divide everything by I. Here.
Okay.
Same thing. So basically the same diagram. Same diagram.
Okay.
Right?
Where does that equation come from? Oh, the tangent of phi equals XL minus. Oh, XL minus.
Yeah.
Okay. Gotcha. Okay. All right, and then
What is T1?
right.
The first time after T is equal to 0 and the voltage across the inductor is 0.
Yeah.
So we have V now.
Oh.
And the first time after, do you know what does it look like at T equals 0?
What is? Which one?
What everything looks like at T is equal to 0. Well, it's described by sine. Oops. This is times. Sine omega T is equal to 0, it's equal to 0, right?
Right.
Yeah, it's equal to 0.
Yeah.
So the first time after
T was 0.
After T is equal to 0, when the this is this EMF.
Right.
And this is going to be plus 90, right? Because it's
Right.
90 degrees ahead.
Wait, hold on. Wait.
This is your angle, right? So at T equals 0, this is how it's oriented. Oh, no, it's not. I'm wrong. I'm going to assume that when you found everything, this is VL, this is VC, and this is VR, and this is
So that's 0. Okay.
EMF, okay? This is at time T equals 0 because it's a sine. The sine is 0 is 0, right? Because it tells you the function of the EMF is going to have a sine omega T. Right? This is sine omega T at T equals 0, sine is 0, right?
Okay.
So at time T equals 0, it's 0. And they're asking the first time when this goes to 0. Remember, this is just spinning.
Right.
And as it spins, it's drawing those 1, 2, 3, 4 sine or cosine waves, right? This is drawn as a sine wave because, it starts to spin like that, then goes down. Right?
Do the lengths of them ever change as it rotates?
Their lengths here, no, they don't.
Okay. But
It would make sense if they did change this. Because their lengths don't change at all except if you change the frequency.
right. Okay.
Frequency don't.
Yeah. Okay.
As time goes by, nothing matters.
Okay. I think that's the biggest thing that's tripping me up is the fact that it's in.
They in circuits 1 and 2 also they say frequency domain. No one ever says why. What is frequency domain?
Right.
Everything's a function of frequency. That your impedances are a function of frequency. Everything changes if you change the frequency. Nothing else matters. No one ever tells you that. Sad. It's really sad.
Okay.
Okay, so we're looking at this becoming 0. You got it.
Okay.
Basically, you got it.
Okay.
I don't have to say anything, right?
Okay. And then
When
so
this
you just
goes, so
find
the
that
same.
angle.
Yeah, you have to know how much time. Well, this is not feet. Oh, there. So how much time you need to cross the arc, which is always how to find it, right?
Okay.
It's obvious how to find it, right?
What?
It's obvious how to find
It's
it.
obvious?
I mean, the time they need to
Right.
rotate from here to here.
I mean, it's not obvious. Well, okay, hold on. Time that it's going to take me to go from there to there. Hold on. Hold on. That's fine. The clocking correct?
Yeah. So it's already. It's supposed to have atomic clocks.
The one in physics is atomic, but it
Was it?
yeah, but it kept
Spinning?
yeah. That's the thing is it only has 2 buttons.
Yeah.
One to like reset it,
Right.
and the other one to like turn it off or something. I don't know. Yeah. So like when you reset it, that's when it starts like spinning.
Yeah. Well, it's looking for a signal or something.
Right. Okay, I'm sorry, my brain is clogged.
You have omega.
Yeah. Right.
which corresponds to
The frequency.
how fast you're spinning.
Right.
Because it corresponds to how fast you're creating beats.
Mm-hmm.
The faster you're spinning, the faster you're creating beats, right?
Mm-hmm.
So omega is basically how many radians you go in a second, right?
Right.
Radian frequency.
Mm-hmm.
Changing angle over change of time.
Right.
So you know omega,
Right.
you know your angle.
180 minus. Okay.
Because this is your, well, where's your phi? This is your phi, right?
Right. Yeah.
Yeah. I mean, it may be negative in your answer. I assume it's positive. It may be negative. If your VC is greater, it's going to be negative.
Okay.
This is going to be here. Okay. And it's sorry, it's going to be.
Okay. Okay. I think I didn't understand how phasor diagrams work. Now I understand.
There's a bit more to it. But yeah, I mean, it's good enough for now. For physics, it's good enough.
Okay.
When you guys start to see it again. I mean, I didn't teach you. They're not going to tell you what it is, but please search. When you're going to ask.
What?
When you get to search.
Search for what though?
Like, what everything means.
Okay. All right.
They're just going to teach you how to use them.
Okay. Okay.
They're pretty easy to use, so I don't know why you're spending semesters teaching people how to use them.
Okay.
But I mean, whenever you get to a concept, just look what it means.
Okay.
Try to get it.
All right. Cool. Okay. Gotcha. Okay, and then I think I had one more question. How did this? Okay, voltage across capacitor. It's pretty.
Where?
The last question, number 6.
What is VC? VD minus VA, the voltage across the capacitor at time t equals 0. D minus VA, okay. And it's
T equals 0.
t equals 0, okay. Yeah, what is it? This is, I mean, assuming this is right, if, I mean, it's in this orientation, assuming the phi is positive, this is how it's going to look at time t equals 0, right?
Right.
And this is your VC.
Okay.
It's magnitude 3.
Okay, but I thought it would be 0 because the total voltage is 0 at 0 or at t equals 0. The the EMF made by that is 0 at t equals 0, right?
Yes.
So I was thinking that.
But the voltage across the capacitor and the inductor are out of phase with the EMF.
Okay.
So they're storing voltage. Remember, there's energy storage, there's storage elements.
Mm.
So the EMF may be 0 because it's flipping, but the things that are out of phase, I'm not going to draw the other one. I'm confused already by it. So at time t equals 0 here, for example, or here, whatever. Remember, this is steady state. It's not actually time equals 0. It's probably time t equals maybe 2, 3 milliseconds.
Oh.
Because that's when steady state actually starts.
Okay.
It's the second you close it, it's going to be 0, yes.
Okay. Yeah.
Right?
Right.
Yeah. If you have a circuit,
Yeah.
you attach it,
Yeah.
it's going to still get up to whatever.
Right.
But after a few oscillations, you're going to have energy stored in your capacitor. At any given time, that energy may be 0 because it goes up and down.
Right.
And energy stored in your inductor also goes up and down. And your guy here goes up and down. Right?
Yeah.
Or it's oscillating. I mean, and during time, you still may have voltage across your capacitor.
Okay.
It's stored from previous periods, these previous oscillations or rotations, whatever you want to call them.
Right. I need to review this stuff. Like practice. Could you go to the second problem? I think there was. Yeah, wait, hold on. Sorry, wait. 2-1. Voltage across the inductor is maximum. So let's just run this point straight up, right? Sorry, for number one, the first question actually was one that like had me confused at first, like when I first read it.
Yeah.
Right. Because so is that just gonna be the time when the vector is pointing straight up?
Yeah.
Yeah. Okay. And it starts again at 0. Like the total EMF starts at 0, right?
So you can just AC generator.
It's the same function. It's sine omega.
Oh, it's sine, yeah, sine starts at 0. EMF starts at 0, but again, EMF may be, and you don't know where EMF is with respect to the other one. It depends on your angle phi, which also depends on where C and L are with respect to each other. And they're going to be 90 degrees apart with the current, with the current that this guy's supplying. And the current that this guy's supplying depends on these.
Okay. So, but basically, we're finding, so if this is, if the phase diagram, so it's at 0, right? And then L is like here or something. That's R, that's C, right?
Mm-hmm.
Yeah. So we're just finding this angle this time, because we're waiting for L to be pointing straight up is the maximum.
What is T1 the first time the first inductor is maximum? Yeah.
So basically just this angle right there. Okay.
So your EMF may also be, I mean, if your X is greater, your EMF is going to be here, right?
Right.
So your inductance is going to be something like that.
Right.
And the maximum, in that case, the maximum magnitude is going to be the time, it's going to be the time to get to the maximum magnitude, which is also negative.
So it could be going down.
Yeah. We don't only worry about magnitude.
Right. Okay. All right. Just scroll up. Impedance L. Okay, L was easy to find. L. Maximum voltage.
A lot of this actually doesn't make sense because because of the stuff they ask you. Because maximum magnitude. Usually when you're working with frequency domain, you don't worry about the maximum of something. You only worry about the average of that thing.
Okay.
In the time domain, you worry about the maximum, which is when it's
Yeah.
maximized. In the frequency domain, you only worry about what is it doing with respect to other things.
Yeah.
Yeah, go ahead, sorry.
Okay, PL max, that's just, there's an equation. Or, hold on. I really wish I had around that.
You remember which one?
I like having the equation sheet with me. Alright, hold on. Yeah, okay. I think those were good. Okay, I think now that I know how phasor diagrams work a little better, I think it's helpful. There was one question I had in LC circuits as well. Or in RLC. There was one question.
RLC, yeah.
I think it was the interactive example.
The other first one.
Or that one. That one, actually.
This one?
Yeah.
Okay. So they want the energy stored in the circuit elements.
Right. So I know the equation for the circuit elements.
That's only the capacitor inductor, right?
Right. 1 over 2 I squared L, and then T squared.
Yeah. So you just want to find
I.
voltage
And
values.
Q. I and Q, yeah. How do you find I and Q? That was
How do you find I here? We're worried about the switch has been open for a long time for it is closed at t equals 0. No, a long time after the switch is closed.
Right.
So steady state.
Yeah.
Start using that way. So at steady state,
Right.
what happens? What happens to the inductor? After a long time, it's completely charged, right?
Yeah.
So
it's a wire.
yeah.
Yeah.
So it's a wire. And the capacitor?
It's open.
Yeah, it's open.
Is it open?
Yeah, it's open.
Okay.
Why wouldn't it be? Yes, it's going to be open if you didn't have this resistor.
Okay.
Okay.
Okay. Okay. I don't know why I thought it would be. Well, okay, because in the example in class, he said that like.
It depends on your circuit. Well.
Yeah. Right. Yeah. So if R4 wasn't there, it would.
Yes.
Okay.
It wouldn't be open.
Okay. Okay.
Why wouldn't it be open?
Only if R4 wasn't there.
Well,
I guess that's what.
I guess you have also R2 here to consider. Hold on. Let me think. If R4 wasn't there, I think it would still be open, would it? If R2 and R4 weren't there, it definitely wouldn't be.
Mm-hmm.
You're talking about this one.
Yeah. Yeah. But when you know.
And I don't know where you have a resistor here, for example.
Or something. Yeah.
Yeah.
That was the one where it was so it didn't become open. Just after a long time, it became nothing.
Right.
Yeah.
Because look what happens. You start charging, right?
And that becomes a wire.
All current comes and it goes here first.
Yeah.
After a while, this becomes a wire,
Mm-hmm.
which means this capacitor also can push current across it. Right?
Okay.
So if you didn't have R2 and R4, it wouldn't be open.
So what's the reason that the same thing can't happen in this case? Is it just because there's resistors there?
Yeah, because the capacitor can. So
I want to explain it in some way, but I want to say it's not. This is not literally what's happening, but you can. I guess you can pick it up this way. I'm going to say the wire is not, because if you have resistor, the wire is not picking up. You want to imagine this was happening. The wire is not picking up to be able to handle the current from this, and it's because they're both going to be trying to push current here.
Okay.
Now, when you remove this resistor, we're assuming this is already gone. When you remove the resistor, the wire has basically no resistance, so it can go. See, in reality, it's not discrete. It's not either open or closed.
Right. Yeah.
There's,
I got that. Yeah.
I mean, it's not always zero or infinity,
Right.
or somewhere in between. It's somewhere. It's always somewhere in between.
Right.
Like even if you actually had it here, because you're going to have a resistance here.
Mm.
Like you're going to have resistance across the inductor.
Right.
So there's going to be voltage across it. It's not actually going to be closed or open.
Yeah. Okay. Okay. It's just that in this case there's significantly less resistance, so like the amount of current that goes through it is so much more than the other one.
So I mean, this is short circuited, right?
Yeah.
And this guy's pushing current here, and this guy's trying. So when it's charged,
Mm-hmm.
what it's basically trying to do is trying to push as much current here as this guy's pushing. I mean, in the original thing when we didn't have an inductor, right? It became charged. This is trying to push current here. This is trying to push current here. Therefore, no current. Therefore, open. Right?
Mm-hmm.
Now you add a wire here, which is what happens in the inductor after a while. This guy is pushing all his current in this loop.
Mm-hmm.
So there's no more current to try to stop this current. Right?
Okay.
So this also goes here. And this becomes uncharged.
Okay.
And there's nothing to charge it anymore.
Right.
Because all your current is going here.
I'm curious, although I don't think we have to know what happens in between.
And you see?
Okay. So
There's going to be a maximum value that it charges to, and then it starts.
Do we have to know that? How to find that?
Uh,
Or is there a way to find that?
there should be a way to find it. I think you can use differential equations to find it.
Okay.
Well, yeah, you can you can create, we want the maximum value of the voltage. We can just write an equation for the voltage of the capacitor and maximize that. It's going to be a differential equation, right? It's going to be a differential equation, and you can make it in terms of I. That's one way to do it. By no, you don't know analysis. Well, KVL, something similar to KVL or KCL. You can take KCL here and write an equation for those currents, then solve those currents in terms of, solve those currents in terms of the voltages, and come up with a differential equation. And solve the differential equation is going to be a function of time. Maximize that function of time. And you maximize the function of time, that's going to give you the time when the voltage across the capacitor is maximum. So the voltage across the capacitor is going to start increasing until something happens here and it starts.
Okay.
Other direction.
So then, okay, so after a while that becomes an open circuit, right?
Yeah.
And then the voltage across that, or actually, no, yeah, so to find the charge, you need to know the voltage, right?
Find the charge.
The charge for the equation,
Yeah.
for the
Find the
energy
charge,
equation.
yeah.
Yeah. So the voltage across it is just the voltage across, like, those two things in parallel, right?
R4.
Yeah. R4 and R2 in parallel.
Yeah.
Or just R4.
Yeah, well, yeah. Voltage here is the same voltage here.
Okay.
And actually, if you know the voltage here, you know everything else. It's easy enough to find out. The voltage here, you know the voltage of the capacitor. You know the voltage here, you know the current. So we got it.
I think it was finding the
What?
I think maybe it was finding the voltage incorrect. Okay. I think
I gotta say this.
sweet.
What's up?